welcome to the second part of the lecture on problem solving on expertise, and now we will start looking at theories of problem solving, and we will discuss the first three theories in this video, and then the next video the last two theories. Let's start with behaviorism. And in behaviorism, the idea is basically a trial and error approach. And if you remember, in behaviorism, the idea is that it's all about reinforcement. So somebody shows, or an animal shows a behavior, and if you reinforce it, it will show that behavior even more. And I would like to start that with a little video clip illustrating that.
But how is a new skill learned? That was a question which began to fascinate Thorndike. To answer it, he built some ingenious puzzle boxes from which cats could only escape by operating latches.
And in you go.
The cat appears to be very clever in engineering its escape, solving the problem with a deftly placed paw and a push of its nose. But Thorndike didn't believe that an animal, even a clever cat, understands the consequences of its behavior. When he placed a cat in the puzzle box for the first time, Thorndike was unable to see any evidence of flashes of insight. The successful actions appeared first by chance. He proved that the apparent cleverness arose by trial and error, and used graphs to measure the rate of learning. A well-practiced cat quickly recalls the actions that help it escape to its reward of food. If an action brings a reward, Thorndike believed that that action becomes stamped into the mind. In his thesis, he explained further his ideas about learning, that behavior changes because of its consequences. He called this his law of effect, which explained how even wild creatures develop new habits.
Okay, so let's go through Thorndike's experiments, and he placed cats which were rather hungry inside such a so-called puzzle box, and the cats had to pull a lever to get out, as we have seen in the video clip. And initially, they showed just random behavior until by chance they pulled the lever. So that's trial and error learning. They just behave and show some random behavior, which then suddenly has a success. And then slowly they learned that their action solved the problem of escaping and getting out of the box. What's noteworthy is if you look at such a learning curve. So here on the y-axis we see the time to escape in seconds. So 600 seconds are 10 minutes. And here the number of trials. So it slowly goes down, and after 12 successful escapes, it's still more than 200 seconds. And then it goes back to 10 minutes again, and then down. And you can see that the learning curve is actually quite slow. So many trials are needed. And this is something where a human might learn this in a single trial. So to look at this trial and error learning, which has been well investigated in the context of behaviorism, it's really characterized by repeated and varied attempts. So I try something, doesn't work, I try something else, doesn't work, I try something else, doesn't work. And it's unsystematic. the person acting usually doesn't have any insight, they don't have a theory of how it might work or result in something, or no organized methodology. The advantages are that we don't need any specific knowledge to do that. We can just give it a try and give it a go. So it's often, trial and error learning is often used actually by animals and by children who don't have these insights or theories or have learned already some methodology to approach problems. The disadvantages are obviously that it can be very tedious and time-consuming or monotonous to try out every time the same thing without any system. And it's potentially risky. So if you want to repair some electric device and you want to learn by trial and error that you first have to unplug it, then this is really, really dangerous. You should have, hopefully, the knowledge and theory of electricity that you should do that. So in adults, trial and error learning is often just the last resort if no other methods are available. Okay, that's all I want to say about the background of behaviorism and trial and error learning. Let's turn to Gestalt Psychology. And you may remember Gestalt Psychology from our lecture on perception, where we said, oh, we have these laws of grouping, law of proximity, and these. But Gestalt Psychology was actually a larger branch of psychology which looked also at other things besides perception, such as problem solving. And an important researcher in this area is Wolfgang Köhler. And what he did, he worked with monkeys, with chimpanzees, and he placed food in the cage or near the cage, which they could reach only by using tools. So, for instance, they had sticks in the cage to try to reach the food, but the sticks on them by themselves are too short. However, they would be long enough if you stick them together to create one long stick. Or he used boxes which needed to be stacked so that something hanging high was reached. These were the kind of experiments he did with the chimpanzees. Now, when observing the animals while they tried to solve the problem, he often observed the following kind of behavior. Like the monkey would try initially, but would fail, because for them it's a difficult task. We just have seen the learning curves of cats when just pushing a lever to get out of a box. Then, at some point, after a couple of failed attempts, the monkey would get frustrated and may retreat into a corner of the cage, sitting there for a while and seemingly doing nothing. And this phase has later on been termed incubation. And then suddenly the monkey would jump up, would rush to the sticks, put them together and solve the problem. And this has been termed insightful behavior or an aha experience or illumination. These type of words have been given to that. And let's have a look at a more modern version of that, how a monkey shows such an insightful behavior.
At the Max Planck Institute for Evolutionary Anthropology in Leipzig, Germany, psychologist Joseph Cole places a peanut inside a clear tube. How can the chimpanzee get the snack? She's never seen this puzzle before.
For 10 minutes there is no solution inside, and all of a sudden, boom, they solve it. They have to understand that they can use the water as a tool. This is interesting because the water itself, it doesn't have any shape.
Using water as a tool seems like something we would do on a good day.
Yes, I can only subscribe to that. On a good day, I find that pretty impressive and challenging to think of filling it up with water so that the peanut floats up and is doing that. So if you remember back the perception lecture, we said that one of the key principles or ideas of Gestalt psychology is the assumption that the whole is different from the sum of its parts. And the same holds basically also in problem solving. The example here would be that two items which I initially considered to be separate, two distinct short sticks, that I can integrate them and put them together into one bigger item which may serve the purpose I need it for, so that again the whole is different to the sum of its parts. When I try with one stick or the other stick individually, I don't reach it. Only when I create a new whole, then I can solve the problem. And this process of putting two sticks together to create one new tool is called mental restructuring, or creation of a new representation of the problem space, the tools I have to solve the problem. And this restructuring, this creation of a new experience, of a new representation, that is, when this sets in, this is the point of an aha experience, or this illumination process. The idea of that we have to restructure our representation to solve the problem has also been used and investigated by Meyer in his two-string problem. And that's the task for the participant. Two strings are hanging down from the ceiling, and the task is to tie them together. However, the task is made challenging, the problem is created by the fact that the strings are not long enough to grasp them both at the same time. So you have to think of something. And here is another little video, the last one for this part, where you can see how people try to do that, to solve that problem.
You can take this test right from your living room.
This is a simple game, really. All you have to do is tie two ropes together. But the problem is these two ropes don't easily reach each other. So that's going to require you to come up with a creative solution. You have the chair, paint can, and a pair of pliers that you can use to solve this problem.
Take a second and consider what you would do to tie this 5-foot rope to this 4-foot rope. Keep trying as these college students also take on the challenge.
You understand what you have to do?
I gotcha.
Tie the ropes together?
Yes.
You can't reach both ropes from the floor, but simply standing on the chair won't help. You're going to have to get creative.
I'm going to tie the chair.
Okay.
Okay, if you want to, you can pause the video for a quick moment and think about yourself. How could that be solved? Okay, let's continue.
Seem impossible? We assure you it can be done.
Yeah, it's not going to work.
Do you feel like giving up too? Well, before you do, let's find out what might be standing in your way.
When you're trying to think of the uses for the objects in the room, you have a hard time thinking of a use that you haven't encountered in your lifetime.
You're not born knowing what a paint can is, but over time, you form associations, such as what a paint can looks like and how it works. Object association is an activity that takes place in a region of the temporal lobe.
If we can prime people to think of a can of paint in a completely different way, that can really help us solve the problem instantly.
So, how does this apply to the ropes challenge and the objects provided? First, you have to add weight to one rope to create a pendulum. What can you use for weight? Here's where that creative thinking comes in handy.
You've gotten very close. You're very close.
Swing the paint can pendulum. Then, while holding onto the other rope, stand on the chair and catch the pendulum as it swings in your direction. With the ends of the ropes now in close proximity, you can release the paint can and tie the ropes.
Yay! Okay. You got it. Yeah.
Did it.
Good job.
That was not easy.
Have you ever used a paint can as a pendulum before?
No, I have not.
Is it the first time?
Yes, it is. I need to get in the gym. I did that. Yes.
Congratulations on completing the Total Mental Fitness Challenge. The two ropes problem required your concentration to slow down and take in the details, and your mental flexibility to stretch and find a creative solution. You can take this test right.
Okay, so as you have seen, the solution is to tie one object to the string and swing it. And to do that, we have to change the representation of one of the object from a proper tool, like a hammer, to the representation of a weight to be swung, to use as a pendulum. And this problem of us to change the representation is called functional fixedness, because we have this tendency to consider only the usual function of the object and find it difficult to see a new function like a pendulum in there. This functional fixedness has been investigated further in more detail by this study from Birch and Rabinowitz. And what they did, they had two groups of participants, and they had to complete an electrical circuit by either using a switch or by using a relay. The details of that are not important. Just important to remember here is that one group really just used the switch in the function of the switch, and the other group used the relay as the function of the relay. Then they were given the two-string problem with a number of objects which they had, and among the objects were switches and relays. What was observed is that they chose different things as a pendulum to swing. When they used the switch to repair, they tended to use the relay more often as the pendulum, and when they used the relay for repair, they used the switch more often. This, of course, is not in absolute terms, so not that all participants who would use the switch would then use the relay. These are relative differences. And the second thing is that now I forgot what I wanted to say. So this is important, that these are only relative differences. So the idea is that when you use the switch for the relay, your functional fixedness for the switch, to use it as a switch, is stronger. So you tend to use the relay. It's more easy to get rid of this functional fixedness in the relay and move over and use it as a pendulum instead. So to summarize the Gestalt Psychology as part, I think really the big thing of the Gestalt Psychology is that they discovered the importance of the representation of the elements of the problem. How do we represent them in our mind? And also the discovery that there is some kind of insight in humans and animals, interesting enough. However, what Gestalt Psychology did not do is that they specified these phenomena of restructuring and insight, try to describe in more detail what they are. And as for the perception, what they did with the laws of grouping, they didn't provide explanations here in terms of theories, models, or more detailed mechanisms. Okay, let's go to the Representational Change Theory, which will be the last one of this video, and the other two then are in the next video. Stellan Olsen, in the early 1990s, based his Representational Change Theory on the Gestalt terminology. However, different to Gestalt Psychology, he provides a mechanism which explains the processes which are involved in this moment of insight in the change of the representation. And the two main processes are the internal representation of the problem, this change of representation which we talked about, and constraints relaxation. And we will have a look at each of them now in a moment. So, internal representation of the problem. And this is good to illustrate with an example. And one of the problems which have been used in research is called the Mutilated Checkerboard problem. Suppose you have the following problem. You have a typical chess board, a chess checkerboard. And this has 8 by 8 squares, so in total it's 64 squares. And now you take away 2 diagonally opposite squares from that square. So 32 squares are left. Now you give the participant 31 domino bits and pieces, and each of these dominoes covers 2 squares. So in theory you have enough. 31 domino pieces will cover the 62 squares which are left after removing 2. And the question now is it possible to cover all of the remaining 62 squares with the dominoes? You can think about this for a moment and pause the video. What most people might do is use such domino pieces and just try it out. Try and error, and just fill that up and see, okay, with my 31 can I cover everything? And then you may come to a situation where you see, okay, there's no way I will be able to cover that with my dominoes, because if I put one here I can't cover that one, if I put one here I can't cover that one. But that was only one attempt. Maybe I can try a different one. The point is, when you try it for a while, you will realize, okay, it never works, but there are literally million different ways, and well, actually it's nearly 1 million possible ways of how to arrange them. You can't solve it by trial and error. So you have to try to find a new representation of the problem and its elements. So how could such a new representation look like? And one representation would be, let's count the number of white and black squares. Well, in this image they are blue, but on the standard board they are black. When we look at dominoes, we will realize no matter how we place the domino, we will always have to do that horizontally or vertically, it will cover 1 black and 1 white square. So that when we have 31 dominoes, we will be able to cover 31 white and 31 black squares. Now let's look at the board itself. Originally it consists of 64 squares, 32 white and 32 black. When we then remove, we set 2 diagonally opposite squares. It will remove 2 white squares, or if I do it the other way around, 2 black squares. That would leave 30 white squares and 32 black squares. So that's what's left on this mutilated checkerboard, and that's what we can cover. And then without any trying out, we will see that it can't be solved. It is not possible to use the 31 domino pieces to cover every field in that checkerboard. Another way to achieve a different representation is to simplify the problem in a way that we change the size of the checkerboard from 8 to 8 to 2 by 2 to make it easier to grasp. And then we may already realize, oh, wait a moment, there must be a diagonal element which I'm not allowed to do. Or you may do it to a 3 by 3 and then get the idea. So in general, taking something complex and reducing it to make it simpler, change the representation to find the solution to that. So that's quite a good mechanism which explains the process involved in insight. And we said there are 2 processes: changing the internal representation of the problem, which we just spoke about, and the other one is constraints relaxation. So let's have a look at this constraints relaxation. An example is the so-called 9-dot problem. Suppose you have these 9 dots in a matrix, and your task is to join all 9 dots by drawing 4 continuous straight lines without lifting the pencil. And just to give you an idea, it could be something like that. You may start here, go 1, 2, 3, 4. You didn't solve it because there are 2 left over. Or another solution might be this one. You may start here, go up, go here, go up, go here. Again, 2 are left. So you can pause the video if you like and give it a try for yourself. Okay, let's continue. So the example, we see that pattern. And if you remember the Gestalt laws, these 9 dots form the shape of a square. And most people automatically assume, put up the constraint, that one has to stay within this square shape. But that's not correct. That was not part of the instruction, and that's not required. So the solution to the problem is first move, second line, and this is the tricky one. We have to go over. We have to overshoot, so to say. And do that again. And then we have 4 lines, 1, 2, 3, 4, connecting all, covering all 9 dots. So for this solution, to see this solution, to realize it, we have to relax the constraints of staying within the square to allow to solve the problem. And quite often these constraints are self-imposed. So we really have to check. And this might be where this phrase, think outside of the box, may come from. You know, we typically have a box around us and we try to think inside the box. Another example is the Majestic Problem. Suppose you have that equation. So in Roman numbers, this is the number 4 equals 3 minus 1. This obviously is incorrect. And the question is, or the task, or the problem is to produce a correct equation by moving exactly 1 matchstick only. Again, feel free to pause the video to give it a go yourself. Okay, let's continue. To do that, the constraints relaxation hint would be consider not only the numbers but also the operators, the plus, minus and equal signs. And if you haven't solved it so far, you can give it another go now and pause the video for a moment. Okay, so the solution is 4 equals 3 minus 1 was the original, to put 1 matchstick of the equal sign and put it over here. So that now we have 4 minus 3 equals 1. And it's a correct equation. Okay, to summarize the representational change theory, it's based on Gestalt principles, but offers a more detailed explanation of how this insight, which Gestalt psychology discovered, can actually be achieved. And the mechanisms are changing the problem representation and to relax the constraints, which we quite often impose on ourselves. The limitations are that still it is unclear how we do it, how it's exactly done to change the representation. So at what stage and in which way? So you may say with the checkerboard problem, yeah, that's all said, well and done, but I would have never come to the idea to reduce it to a 2x2 square checkerboard or to count black and whites. So, but knowing the principal idea that we should change can help to say, I can't solve it that way. In which other way could I represent the problem? That could be a generic strategy. And there are actually many more factors which affect our solution finding in these type of insight problems, like the incubation period, which we have spoke about, that it can be helpful to leave it aside for a while and only then come back, and then we suddenly see the solution. And the representational change theory doesn't make any statements on these other factors. If you have questions, please post them on the BBL discussion board. Thank you for listening. This was a little bit longer go, but the next ones should be shorter again.